Hey, it's Stereo Police. Back with another part of the series on the H. Scott Stereo Master 222B. And in this video, in the previous video we talked about the theory of operation of the amplifier section. And again, just to step back, this amplifier I purchased pre-owned, and before I hook this up to my good speakers, given that this amplifier is circa early 1960s, it's been refurbished by an unknown technician. So before I hook this up to my good speakers, I always like to get a look at the signal on the scope, see what's going on, and put a waveform into it, get an idea what's going on with regards to how clean the signal looks, and just get an idea about total harmonic distortion and see if it jibes with the specifications. See if there's anything funny going on. And one thing I'm not going to show you that I do is I like to look at the signal as the when I first turn the amp on, and then I watch the signal as the tubes heat up to see if there's any spurious signals, any static, any noise, any spikes, any transients, that kind of thing. It gives me some idea about the condition, status of the tubes. And there was just a little bit of jumpiness there going on, nothing completely out of the ordinary, normal for old tubes warming up. I doubt anything that'll be audible. So here we go. This amp has been running now for about an hour, and I have hooked into it. I've got an audio generator, and I have it set at 1 kilohertz and a 1 kilohertz sine wave. And I've got it plugged into the tuner section, and I have the tuner section selected. And I have the speakers hooked up to an 8 ohm dummy load, my power resistors here. These are 100 watt power resistors. However, they're not hooked up to the necessary heat sink, so I don't run them at anywhere near 100 watts. I can spike them occasionally, but I cannot run them at 100 watts. So, in this case, I don't expect to be getting anywhere past about 11 to 15 watts, so it's no big deal. And I'm scoping both channels, and as you can see, that's what we have here. And as I rotate the volume knob left and right. Okay, so we're going to do a couple of tests here. And the first test I like to do, and we're going to do a couple of different, and by the way, the signals look nice and clean. Left and right channel. I'm controlling the balance right now. So I'm rotating the balance left. So you can see the right channel is the yellow trace. Now I'm rotating the balance right, and the left channel is the blue trace. It's syncing on the yellow, so that's why that happened. Okay, so one of the things I like to do is, in old equipment, I never trust a balance knob. So I like to find out where exactly on the balance knob the two signals are exactly equal. So what I'm going to do is I'm going to put these two signals right over top of each other. Just like that. And I'm going to control the balance knob so that they're identical in amplitude. And there I have it. They're right over top of each other and identical in amplitude. And let's see if the balance knob is dead center. And as you can see, it is not dead center. That's the bass, I'm sorry. See that? Not dead center. It's somewhere between 0 and 1 counterclockwise. So now I know when I'm listening to this amplifier, that's where I need to keep the balance knob. If I were to rotate, I don't know what I just did there. I accidentally hit a button on my phone. I don't know where I left off, but we were talking about the balance knob being offset. So I suppose I could just pull that knob off and reset it. I don't know if these have set screws or not, but I'm just going to leave it alone for now. But if I were to have that balance knob exactly at 0, then you can see the left and the right are not exactly at the same level, a little bit off. Pretty close though, but not exactly off. So I'd prefer to know that I'm going to leave it between 0 and 1 counterclockwise. And they are dead smack equal and level at that point. And you can see, looking at the RMS, yellow RMS voltage, one of them is 325, the other is 323. They're the same level. Let me go back and rotate. Now see, I'm offset between 0 and 1 counterclockwise. Let me rotate this back to 0. And now look at the RMS voltage. One of them is 347, the other is 323 millivolts. So that's good to know. I never trust a balance knob. I like to know where my true balance, where my true center is. All right, so let me rotate that back. Okay. And all right, and I see these do have set screws. I may be able to use this, take that set screw off and reset that knob. I'm probably not though, because those potentiometers have a flat on them where that set screw goes. Probably it's just the way it is, but that's good to know. All right, now I like to know, I believe the specs said that this amplifier produces, let me double check the specs on this. Let's find out where this amplifier starts distorting. Total harmonic distortion. Alright, according to my spec sheet, maximum power at each channel is going to be at 13 watts at 0.8%. 13 watts at 0.8%. So I'm going to do this 3 ways. I like to have fun doing this 3 different ways. I'm going to do this visually, 2 different ways visually, and then the 3rd way is going to be using the Keithley THD meter to get the more accurate THD at 0.8%. So let's find out. Okay, looking at the specs, 13 watts. It's rated at 13 watts. Given that I have an 8 ohm load, it's a purely resistive load, and given our equation for power, that means I should achieve 10 volts RMS. 10 volts RMS across the 8 ohm load before significant distortion. So let's go ahead, and I'm going to turn off one channel, and we're just going to look at one channel and look at the sine wave and see what that sine wave looks like at 10 volts RMS. and you'll be able to see it down there in the yellow RMS. I'm going to start turning up. That's 3 volts RMS. Okay. Let me disconnect one channel here. All right. Look, we're looking at blue now, so there's 7 volts RMS. We still have a clean sine wave. And there we start our clipping. You can start to see significant clipping, and you can start to see crossover distortion. Let me move that signal away from the gradical there so you can see the crossover distortion that starts happening when we approach that point. Okay, you see that crossover distortion? And then I'm going to back down right before we start to see any kind of visible distortion, and we have about 9.21 volts. 9.21 volts. I can sort of see the visible distortion, but about 9.21 volts. And that is fairly consistent with our 10 volts. But again, we're just going visually here. Now I'm going to switch out the probes and look at the other channel to see if that's fairly consistent. Okay, we're now looking, even though it's the same color, we're now looking at the other channel of the amp. I switched probes, and there we're starting to see that crossover. As I go way up, we're seeing the clipping. You see that? And because they're vacuum tubes, it's not hard clipping, it's soft clipping, then we go into hard clipping. So I'm backing down, I'm crossover, back down, right about there. That channel's a little less. 7.8, close to 9. Close to 9 volts. So one channel's a little weaker than the other. However, that could be explained by the fact that I have 2 sets of tubes. One set of tubes is an original Fisher pair, the other set of tubes is an Amperex pair. So that's why I like to have a full complement of matched output tubes in my amplifier, which I do have on order, by the way. Alright, so far so good. Now, let's get a look at let's do the same kind of thing, but look at it in the frequency domain. Okay, here I have one channel of my amp set up, and you can start to see where there's our clipping. There's our crossover distortion right there. I'm controlling the volume now. So let me go down in amplitude to where there's no visible distortion, and we're going to do a fast Fourier transform. And on the left there is the fundamental, that big spike is the fundamental frequency on the left. And as I turn up the volume and we start to get that distortion, you'll start to see the harmonics. There's the harmonics right there. And I'm going to turn up until I start seeing a big bump in those harmonics. Right, let's say right there. And let me jump back over to channel 2 and see our RMS. That's 7.2 volts RMS. So I start to see a big jump in harmonics at 7.2 volts RMS. So that's one channel. And let's see. Let me switch probes to the other channel. That's the other channel that was the stronger of the channels. And we're going to do the same thing. I'm going to back down to where we don't have any distortion. We're going to do an FFT, and where I see a significant jump, and those harmonics are different than the other side. See those? These harmonics are fundamentally different. This, you can see the distortion on this channel is odd harmonics. The other one was even and odd. Well, that's interesting. But let me go up to where I get a significant jump in harmonics and then see what kind of voltage we're dealing with. And on this channel, 8 volts. 8 volts. 8.0 volts RMS. So if, okay, I stopped just to run some numbers. So given that power equals V squared over R, I cut these two channels down the middle and just said, well, roughly 7.5 volts, just going visually off the fast Fourier transform, before we start seeing a significant jump in harmonics or harmonic distortion. So 7.5 squared over 8 yields 7 clean watts. 7 clean watts before we start seeing a significant jump in the harmonics. I still have no idea what percentage of harmonic distortion that is yet. I'm just going where those, I'm just looking at visually at the FFT where those harmonics start to jump. At that point, something bad is starting to happen. Whether it's crossover distortion or whether it's the tube starting to soft clip. But at that point, something is really starting to break down. So I'm calling it, and also I could tell you based on the harmonics, one channel is distorting differently than the other channel. I suspect, one channel, let me go back and show you this. This channel, and I don't care whether it's the left or the right at this point because I'm getting all new output tubes. I'm going to run this test again, but I suspect it's the fact that we have different output tubes. But let me run this again. All right, I'm going to take a snapshot. All right, I just took a snapshot here. Take a look. Here we have our fundamental, and then we have our second harmonic, third, fourth, and fifth. So this is an even harmonic, that's an odd harmonic. So our even harmonics are lower in level, our odd harmonics are popping up higher. Now that's one of the two channels. When it first starts to distort, it's mostly high in the odd harmonics. Now I'm going to switch channels. When I say switch channels, what I mean is I'm switching the from the left channel of the amp to the right channel. By doing that, I'm just switching probes. I have one probe on one channel, one on the other. And then let's run that test again. Taking a snapshot. Now this is the other channel of the amplifier, and look at how this channel distorts. It's second harmonic, third, fourth, like in a stair step. It's all the harmonics, even and odd. So they're distorting differently. But like I said, once again, I've got two different sets of output tubes from two different manufacturers, perhaps manufactured at different time periods under different conditions. I have no other way to explain that, at this point at least. I have not opened the bottom. I have not done any other probing of this amplifier. Now, I don't really care that much because for the most part, when I'm running this amplifier, I'm not running it to this level, hopefully. Hopefully we're running this amplifier far less than the wattage that would produce this. Now, so what I'm saying is right now I've got about 7 or so clean watts before before we see the harmonics start popping. That's interesting. Now to put it on the Keithley and find out. I'm going to do the same test, but run it up to where the Keithley says we're at 1%. Now the specs says 13 watts at 0.8. 0.8 is close enough to 1. I'm going to run it up to where we get 1% THD, and then look at what output voltage we have, and then calculate the power output across the 8 ohm load at 1%, and see how close that jibes with the specifications. Okay, here we go. The Keithley is hooked up. I'm going to start out. The Keithley will automatically detect the 1 kilohertz fundamental and go from there. So I am going to shift THD, and right now we're at a fairly low level. We're going to start out at 2 volts. I had to rise it up some so that the Keithley would detect the fundamental over the noise. So we're going to start out at 2 volts, which is, I already know from looking at the waveform, there's absolutely no distortion there. So we're going to start out grabbing the THD at 2 volts, and we're at 0.3. And I'm going to slowly increase. So I'm going to slowly increase the voltage, and I'm going to do that as, let me start out at a low level right here. I'm going to start out at a low level, and I'm going to have you watch the Keithley. And we're going to strive for 1% THD. And this is percentage total harmonic distortion. Now it's starting to bump up. There's our 1. Let's grab the voltage on that. 6.3. Let's see if the scope agrees. 6.4. The Keithley is more accurate. So 6.3 volts. At 1% on one channel, and this happens to be this channel here, but I don't care which is which. So 6.3 on one channel. I guess it would be interesting to know which tube set produces the most distortion-free power, but okay, let's switch. You can see this is the Keithley hookup here, so I'm going to switch oscilloscope probes as well as the Keithley over to the other resistor and measure the other channel and see how that works. All right, let's rock and roll. So here's what we're going to, and so that one channel at 6.3 volts RMS across the 8 ohm load at 1% THD. So we take our 6.3 squared divided by 8. That's 5 watts. That's it, folks. That's what we're getting. 5 watts. All right. Let's do the other with the other channel. So I'm starting out. I've got the Keithley hooked up to the other channel right now. And yep, we're hooked up to the other channel. The other channel is also scoped. I'm starting out at 2 volts like I did last time so that the Keithley can grab the fundamental. Nice clean sine wave there. And let's go ahead and start with our THD. So we're starting out with 0.3%, and I'm going to start increasing the amplitude slowly, and we're going to watch the THD rise, and we're going to strive for 1%. And at 1%, we have 7.6 volts, higher than the other channel. 7.6 volts. Turn this down. We have 7.6 volts RMS at 1%. So 7.6 squared over 8. 7.2 watts. So the stronger channel is this one. I'm going to go ahead, I'm done with my measurements. I'm going to turn this amp off. I could take some frequency sweeps. I might do that later and check out the frequency response. I'm running out of time tonight. Go ahead and turn this amp off. So this is the stronger channel right here. And this channel is channel B. Channel B. Now, do I know which channel B is right here? No. I'll have to look at the schematic to figure out. It'd be interesting to know which tube set is producing the stronger output. But like I say, I'm going to repeat this process because I've ordered a matched quad of these EL84s. But this is the kind of thing you run into when you have a mixed bag of output tubes, and why you want to get a matched set of tubes, of output tubes. And even you even want your tubes matched throughout generally for that reason, because then you get differing characteristics. But within the power band, before they start distorting, the signals are evenly matched, other than that balance in match. But you can see we're not anywhere close to the spec'd out 13 watts at 0.8%. Not anywhere close to it. There could be reasons for that. There's a bias adjustment that I might have to explore. There's an AC balance and a DC balance as well. These are all adjustments that need to be made, and perhaps they were not done properly. That I'm going to have to explore, and I will explore those. But that's enough for tonight, folks. I hope you found that enjoyable, and I'll get back to you as soon as I can. Have a good one. Stereo Police. Ciao. Hey, I said ciao a little prematurely because a thought came to my mind about the fact that the THD measurements yielded a much lower power output than the specs led me to believe. A couple of thoughts on that. Number one, I believe that many tube amplifiers were rather overstated. Many vintage tube amplifiers were rather overstated. I've measured quite a few vintage tube amplifiers, and I've yet, even one modern one that I have, as a matter of fact, and I've yet to come across a tube amplifier that actually meets the power handling at its stated total harmonic distortion. That's number one. Number two, as for the cause of it, it could be any number of factors. I alluded to earlier the adjustments, the bias, and there's a AC balance and a DC balance that I intend to do. It could be that. It could be weak tubes. These tubes are unknown to me. I don't know what they've been through. They could be old. They could be weak. It could be weak 12AX7s. It could be weak EL84s. I mentioned I do have on order a matched quad of EL84s. That's the first step. But even if I was to keep this amplifier in its current state, it really is no big deal, and I'll tell you why. One doesn't purchase an amplifier like this to drive low sensitivity speakers. And I'll give you an example. I intend to drive my Klipsch with this amplifier, and my Forte speakers, and I rather want to drive my Cornwalls. So using my Cornwalls as an example, I forget offhand what their sensitivity is, but it's approaching 100. 100 decibels at 2.83 volts input, 100 decibels at 1 meter, and that right there, 2.83 volts at 100 decibels at 1 meter is concert levels, more than I ever listened to. So with that in mind, let's just get an idea, worst case scenario, what the distortion of this amplifier in its current state would be at 2.83 volts. I have my 8 ohm dummy loads already hooked up, and I'm measuring the strong channel right now. I'm going to measure both channels. So I'm measuring the strong channel, which was able to produce 7.2 watts at 1%. But now I'm going to be concerned with only 2.83 volts. So I'm looking at the strong channel, and I'm going to get it somewhere around 2.8. That's close enough, 2.84 volts. And this would, and again, I'm looking at it from the perspective, if I have my Cornwall 3s hooked up to this amplifier and I'm running a signal averaging around 2.83 volts RMS of music, steady state, relatively speaking, through them, I'm listening to those Cornwalls at concert levels, which is not realistic for me. But let's see what the THD would be at this point. 0.3%. Now I can tell you that's an artificially high number because my signal generator itself is at about 0.2% THD. So I'm at this amplifier is actually less than 0.3. A portion of that THD you're looking at is coming directly from the signal source itself. So that's very, very good. So this amplifier as it is, at least in the strong channel right now, is perfectly adequate to drive my Cornwall 3s. Let's switch it over and look at the weak channel to see if that channel is adequate as well. Okay, now I've got the scope as well as the Keithley hooked up to the weak channel being the channel that did produce only 5 watts at 1% THD as opposed to the 7.2. And let's see what the THD is going to be at 2.8 volts. And again, I'm adjusting the volume knob here. Close enough. All right. 0.3 again. So, and like I mentioned last time, the signal source itself is on the order of 0.2% THD, so the amplifier is less than that. Nice signal there. So this amplifier is less than 0.2%, 0.3%, less than 0.3% THD at 2.83 volts across an 8 ohm load, which means I would be able to drive my Forte 3s and my Cornwall 3s at concert levels well within the range of extremely low distortion levels with this amplifier, and that's the point behind this style of amplifier. And with enough headroom. So you know, the fact that we didn't measure out to the full 13 watts at 0.8% THD is really not of major concern to me. But it will be interesting to see what happens when I get my matched quad of EL84s in. So anyway, it occurred to me I wanted to run that experiment after I thought I'd finalized the previous the previous portion of the video. So I thought that would be rather interesting. But that's the point behind this style of amplifier. So thus far, this amplifier is behaving perfectly as far as I'm concerned. So anyway, enough of that. I'll say my second goodbye. Stereo Police. Ciao.